All right, thank you for your patience. So I always start 5 after to give a chance to the students to run in. So thank you everybody for coming for this iteration of the DSS, the CE DSS, the CC May Distinguished Seminar Series. This is a series that fosters talks that are basically high level and broad for the CE community and to bring people from all of MIT and beyond. And we usually cover topics in mechanics, fluid mechanics, transportation, environment, and try to basically build bridges. So if you're interested in the talks, there is all of them are on the website dss.mit.edu. So I invite you to visit, and you can use them for lectures and all sorts of other activities. So for today, we will have the pleasure to have Dr. Madanat that will present in transportation, and I will leave his detailed introduction to my colleague Sorab Amin.
Okay, hello everybody. So it's a pleasure and honor to introduce to you my former professor and mentor from Berkeley, Professor Samir Madanat, who is the Dean of Engineering at NYU Abu Dhabi. And he is Zenil Distinguished Professor Emeritus and former chair of the Department of Civil and Environmental Engineering at Berkeley. So Professor Madanat's interests are in infrastructure management, broadly speaking, but specifically he has made fundamental contributions in modeling of facility performance, including uncertainty in the optimization of infrastructures, investments of infrastructures, and more recently, engineering and policy solutions to sustainable engineering systems. So he is a terrific teacher and has been an inspiration in many ways. So please welcome Professor Madanat.
Thank you very much, Lydia, for the invitation, and Sora for this very generous introduction. I don't know what you mean by being a terrific teacher. Terrific can mean different things. This is the first presentation I've given back at MIT since my PhD dissertation defense, which was in 1991. I still feel the same kind of trembling in my knees that I did on that day. The topic that I'll be talking about is really, I'll focus on the work that we've done, but as part of a larger research project that involved collaborations between a fluid mechanics expert, my colleague at Berkeley, Mark Stacey, an expert in public policy, our colleagues at UC Davis, Mark Lubell, who's very interested in governance networks, and myself. It brings together really these three different strands of research, and we felt that the topic that we wanted to attack really needed this kind of interdisciplinary collaboration. And so we're talking primarily about the protection of transportation infrastructure networks, highway networks, from sea level rises. Is the lighting good? Or? Yeah, okay. So here's the team. So at New York University, my students and postdocs and research scientists and myself. This includes, among others, Aaron Chow, who came to us directly from MIT. He worked with Eric Adams here as a postdoc, and he's one of our research scientists. There's a typo here. Bruce Royorden is actually part of the Berkeley team. I told somebody I prepared these slides on the way, on the plane, so there may be some typos like this along the way. The Berkeley team consists of Mark Stacey, who's now department chair there, Roger Wang, another MIT product, who was a postdoc with Mark, and the UC Davis team. We also had a collaboration with the US Geological Survey. They provided us with Cosmos, which is a calibrated version of a hydrodynamic model, calibrated for the San Francisco Bay Area. And funding came from NSF through the CRISP program and fellowships to PhD students at NYU through the GPPO Global Postdoc and PhD fellowships. Briefly, I'll cover two main topics in the context of our work. I'll start, of course, with some background, general background about what it is that we're doing. And then, I knew it. There'll be we'll start by looking at a kind of a county level analysis. Our focus, our geographical area is the San Francisco Bay, which includes 9 counties that surround, and we're going to take the counties as units of analysis and of decision making in the first part of the presentation. And then some more recent work that we've done with more finely grained units as units of analysis, which are known as operational landscape units, or OLUs. Which were about a year ago determined or defined for the San Francisco Bay. And we'll show that through things like these OLUs and by using detailed traffic simulators, we're able to separate the effect of hydrodynamics versus the effect of traffic congestion on the total benefits of that we're trying to do. So sea level rise, this is not an audience I need to convince it's happening. These are actually satellite data taken for that period, 93 to 2016. The y-axis is in millimeters, but there have been predictions of global sea level rise ranging from, in 2054, according to IPCC, 0.5 meter, and above 1.5 meter by the end of this century. Our interest, of course, is how sea level rise interacts with coastal infrastructure. Here's a question that if you took no protection, and by the end of the century, we can expect something like 1.5 or 5 feet of sea level rise. So you could imagine LaGuardia Airport looking like this. And this is what we're trying to avoid. In the context of highway, and Boston itself has had some experience in 1996. So the estimate of the damage at that time was about $70 million, probably more if it happened now. In the context of transportation networks, the interruption or cuts to highway links or inundation of tunnels would have impacts that would be expected to actually be compounded by the very fact, by the network structure of highway systems. And in the sense that cutting one link or more in a highway network would divert traffic elsewhere, causing congestion on links that might be already congested or close to congestion. And that essentially is the worry, in particular, which makes transportation networks interesting to study. That network component makes that a small problem in one part or a partial closing of one lane would have effects that are much broader. So the geographical area of the study is the San Francisco Bay Area. That was the focus in our proposal, and we've continued to work on it. So for those who are not familiar, there are 9 counties around the San Francisco Bay, and they're shown here. This is the population of the Bay Area is somewhere between 7 and 8 million people now, I expect. And obviously, this major location for high tech and other industries, inundation of highway networks or parts of the highway network in the San Francisco Bay would have significant effects on the economy, not just of the Bay or California, but the US in general. Now, why is this interesting, and why is it kind of a particularly complex problem? Is because in hydrodynamics, you have interactions between actions that you might take on one part of the bay and other parts. So the map you have here shows, the 4 maps you have show the interactions that can be expected at different levels of sea level rise. Now, what makes, and just to give you an idea, if you look at the topography or at the map of the San Francisco Bay, the Pacific Ocean, of course, is on this side, and then you have this narrow opening, right? And the forcing, the hydrodynamic forcing, comes from the Pacific Ocean and enters here, and this you have something that is almost entirely enclosed. So you tend to see a kind of a multiplicative effect of inundation. Here are some what you can expect with a 0.5 meter sea level rise that, according to IPCC, should be happening in about 30 years from now. You'd see that, for example, in the South Bay, there's significant interactions between the 3 counties here, San Mateo, Alameda, and Santa Clara. So protection of one of them would lead to inundations in the other. At 1 meter sea level, these interactions increase, and also in the North Bay. And at about 1.5 meter, if the predictions are correct, this is what we expect by the end of the century, then you start to see these interactions, not just within the South Bay or within the North Bay, but between the 2 parts of the bay. So that's one thing that makes our problem interesting. The other thing is that we don't have a single decision maker who's in charge of everything. We have multiple decision makers at play in the San Francisco Bay. So you have counties making their own independent decisions, you have some cities within counties making their own independent decisions, and you have other agencies that are responsible, that are trying to get people to talk to each other. And as part of our team, as I said, we have Mark Lubell and his students and postdocs who have done extensive surveys talking to actors, to the decision makers in the San Francisco Bay who are very concerned, whether they be MTC, the MPO, the Metropolitan Planning Organization for the San Francisco Bay Area, or other agencies, as well as to individuals within cities, city government or county level government. And for many cases, they are not talking to each other, they're not sharing information. The level of awareness about the importance of sea level rise is not uniform, and therefore what we can expect is that rather than doing things in a coordinated manner, they might be doing things mostly in an independent manner. And because we're dealing here with our focus is on highway networks, if you protect your own county shoreline, for example, you can expect as a result to make things worse for your neighbors, but inundating your neighbor's highway network makes things worse for you as well, potentially, because congestion, you have basically queue spillback from your neighbor's highway network to yours. Essentially, congestion will propagate through potentially the entire network, but certainly your own. So, because of these kind of complex interaction between hydrodynamics and traffic and governments, this team came together. We are calling ourselves RISER, which is Resilient Infrastructure When Seas Rise. And the problem really is represented at a very high level, in a very high level way by this picture. And essentially we have 3 networks at play here: a governance network, which represents, the nodes represent different agencies, different counties, cities, and the links represent whether they're communicating or not currently. We have the highway network. And we're focusing here only on highways in this phase of the research. We haven't brought in public transportation. I need to say this, though we're starting to look at that. And then the infrastructure protection, that is the levees that you built, which together with the interactions in hydrodynamics create, in effect, another network. And it's the interaction between what happens within networks and across networks which I think are particularly interesting. So, starting with the county level analysis. So here we're essentially taking, though there are decision makers at different levels, in order to have some kind of uniformity, we assume that each county was its own decision maker. And these counties, as I said, and as our Mark Lubell and his team have shown us, have very limited level of interaction at this point. Some are further ahead than others. And the fact that they're each acting, or most of them are acting independently, means that the problem lends itself to approaching it as a game, as a competitive game. The scope of the NYU team is essentially this. So we're going to look at modeling the transportation network problem, and we're going to look at it initially in three different ways. We'll first assume we have a centralized decision maker who's taking actions, allocating resources across counties in order to achieve some kind of social optimal. All right. Then we're going to look at what might be a more realistic case, which is to consider the counties as players. And these players compete in kind of a Nash game, or they might be also enticed to work in a collaborative way. And that is, in fact, what part of our research is aimed at, is at showing the benefits of collaborative actions. And this can be modeled as a collaborative game, which is a branch of game theory that has grown significantly in the past 10 years. Now, a few things I need to say. We are looking at one metric of benefit here, and that is the difference between vehicle hours traveled if you do nothing, and vehicle hour traveled if you take some combination of action. Now, this is one metric of importance to transportation. We're not looking at accessibility, which is another very important metric. But for the time being, that's our focus. So a few assumptions. 0.5 meter. Yes, Monzer.
When you describe a game, you assume that everybody has information about all the other players?
So they have information about the consequences of other players' actions.
It's a Bayesian game.
Yeah, pardon?
It's a stochastic game.
Yeah, no. So it's not stochastic because so if by this you mean that you have a Nash game where you might have like mixed strategy. No, that's not the case. So this is like a pure strategy Nash game, right? And the competitive game as well. So what are the actions that counties can take? They either install a levee or don't install a levee. And we can predict the hydrodynamic interactions by using Cosmos, this system that was provided to us by USGS. And we will look at only 8 counties. San Francisco is excluded because San Francisco can be assumed to always be protected. What is more, San Francisco has very limited, the protection of San Francisco has almost no impact on the other counties. So the size of the problem is reduced, and therefore we have 2 to the power 8 to 56 combinations. Fine. So starting with the centralized decision maker. So this is the somewhat unrealistic but important model, which gives us kind of a baseline. It's like if you had a centralized decision maker, and this centralized decision maker was allocating resources across counties. So a county is either given funding or not. Depending on the budget available. Now, the way we do this is quite straightforward. So you identify the inundated areas by doing your hydrodynamic simulation for each possible combination, each of the 256 combinations. Based on this, you cut the network links that are inundated or that isolated. They might not be inundated, but they might be inaccessible. And you obtain a reduced network. You run traffic assignment on your reduced network by doing user equilibrium. And I see already people in transportation cringing at the thought of still using user equilibrium. So the justification for that is we're looking at kind of long-term inundation effects. These are not short-term floods, for example, and therefore you can assume that the traffic flow pattern in the network is going to reach some kind of steady state after a few weeks, and that is the steady state that we're accounting for. This is why user equilibrium might be, despite all its failings, a reasonable thing to do. The benefit I've already described, and we only include motorways and so freeways, arterials. We don't take local streets into account. So this is essentially how our procedure goes. It's a bi-level model. The higher level model is the decision maker. The lower level model are the users of the traffic network. We have 256 combinations, so it's not a huge number, and there's no fancy optimization here. This is just a very straightforward, complete enumeration of the strategies, and for each strategy, we look at the corresponding cuts. We run user equilibrium on the reduced network. We obtain a measure of the benefit, and then we do the next one. So how do the results look like? So these are the 256 strategies plotted on these two-dimensional plane. The x-axis is the length of protection, which is a proxy for cost spent. Okay, so this is the length of the shoreline that's protected, and the y-axis is the VHT benefit. This is on per trip. So it's the total benefit divided by the number of users, right? So as you can expect, there's a general upward trend. The more the longer the shoreline that you protect, the higher the benefit. And we have a set of combinations of strategies that essentially give us a Pareto frontier, where for a given budget, if you will, you cannot do better than that, all right? Now, what is somewhat, a couple of things that are interesting here. The Pareto frontier contains, for example, here might have a single county, San Mateo, and here a single county, Marin. But near the end, and in fact, at the point where you can assume to have almost unlimited budget, we end up with only 6 of the 8 counties being protected. It turns out that if you extended this line, it would continue to be horizontal up until this last point. And the 2 counties that are not protected here, but are protected here, are Napa and Sonoma. These are in the northern part of the bay, wine country for those who've been there. And their shoreline are in fact the least important to protect. Least important because they do not add any benefit, only cost. And so that's somewhat interesting. What is also interesting is that there's one county which is Marin County. This is the county immediately north of San Francisco, across the Golden Gate Bridge, where we're showing again the 256 combination here, but we have 2 types of dots. The black ones are those where Marin is protected. The red ones are those where Marin is not protected. And we can see that Marin is always in the higher part of the benefit. Now, if one way to think about this, maybe I'll go back to the map. Yes, so if you look at Marin County here, there's actually a single freeway going from north to south. It's Highway 101. And Highway 101 carries traffic from the North Bay to San Francisco and points south. It connects to Highway 580 that crosses here approximately over the so-called Richmond Bridge. And that intersection is very close to the bay. So if that intersection or any part of that of Highway 101 is cut, that's it. This traffic has nowhere to go, right? In fact, not only it cannot just like take the Richmond Bridge because the approach to the bridge has been inundated. In fact, would have to do this, which so the lack of alternatives in Marin County, the fact that the network has very low limited redundancy is what leads to this problem. You will now, jumping ahead, you will see that the other two counties that are critical, actually the second county in terms of importance is San Mateo. Now San Mateo is home to a lot of high-tech industries here. What makes it interesting is that it has two bridges that connect from Alameda to San Mateo, right? And if these bridges are inundated or they approach inundated, then you're talking about traffic that would usually cross, having to drive south through Santa Clara around the bay. So let's take a look at these. Sorry for this. All right. So what we have here, we have different rows, one for each point on the Pareto frontier. And the rightmost point is the one that includes these 6 counties, includes Napa and Sonoma. And here you can see the contribution of each of these counties to VHT reduction, right? And Marin has 50% approximately of total reduction, so that's huge. Second is San Mateo. Now San Mateo itself has an alternative to 101, which is 280, but the problem is that it's not so much if 101 itself is inundated, but the approaches to the bridge are inundated. That creates a problem, all right? So this is important, we will come back to it later. So now moving to essentially a game theoretic approach. So we look at this first as a competitive game, as a Nash game. Now it could be argued that some counties are moving ahead further, faster than others, and maybe a Stackelberg game would be more appropriate. And that's something, in fact, that we started with that, but there's insufficient information about where the level of readiness of these different counties. So a Nash game is probably a good starting point at the very minimum. And again here, here the important thing is that the players are trying to maximize the VHD benefit. That is the difference between the VHT if we do nothing versus a VHT, the vehicle hours of travel, total travel time for a given combination. All right, all right. Now we want to compare this to game theoretical analysis of a different type, that is the collaborative games. And in here there's a possibility for counties to form teams or coalitions that jointly work to protect the coalition itself. And in this coalition, some counties may be contributing fundings, others may not. And those that do contribute do not necessarily protect themselves. If it turns out that for the coalition as a whole, it's better to protect other members of the coalition. But of course, a cooperation like this is only possible if none of the members of the team or the coalition experiences a reduction in benefits relative to that of the corresponding Nash VHT. There's a way to allocate or to divide the funding from each of the participating country, and some of that is based on the work of Shapley, which we made use of. All right, so I'll jump directly to a couple of results that are interesting. A very large number, there's a combinatorial number of potential collaborations. Those that I will show are somewhat some of the most interesting results. And we start with something of an extreme case where only 2 counties in the Bay have the sufficient budget to protect themselves, and nobody else has any money available. So we'll compare the results, and these 2 counties are Napa and Alameda, right? So here's the result of the Nash game in blue. Oh, the y-axis, are the VHD benefits. So, and these are the different counties, and we also look at the total. The Nash game results in blue in terms of VHT shows that, of course, Napa will protect itself, Alameda protects itself. Some people suffer, some people benefit a little bit, but and the total benefit is this, right? Then if we look at the cooperative game, then it turns out that the two counties would pool their resources, would not protect themselves, but would protect these three counties: Marin, Solano, and Santa Clara. Right? They have just enough, they have a little bit more than the necessary budget to protect these three counties. And so the orange bar represents the benefits on a county by county, and the difference in total benefit is quite significant. So this is not a result we would have intuitively necessarily expected, but it shows that because you're dealing with the transportation network, if you protect other parts of the network rather than yourself, everybody gains, including yourself. So obviously Napa gained more and Alameda gained more. If they didn't, they wouldn't have participated in this coalition. Yes?
How do you assign the VHT to each of the different players? Is it
It's
the VHT on the links within that county? Or
excellent
the
question.
origin does
I should have mentioned that. Yes, it's exactly that. It's the VHT of the links within that county. Now, a different approach might be to say, well, will each county counts only about its own residents or people who work here, right? So you could have done, and we thought of doing this as well, and it's a perfectly valid alternate approach, is to say each county is going to minimize travel time within the county only for people who either have their origins or their destinations in the county. So in the morning commute, if you're San Mateo, for example, you have people from San Mateo who are working in Santa Clara, right? And maybe you only care about these people, right? But so, you know, it's not, this approach is not, or this objective is not better than the one you're proposing. It's just the one we did. Now, another interesting thing about these cooperation is that something else happens. This is the available budget to Alameda and to Napa. This is just enough to protect their own shoreline. In the Nash game, they use their entire budget to protect themselves. But in the cooperation case, they're protecting shorter in total shorelines than their own, and so the cost is also reduced, which means they have more money to do other things. Now, if we remove the budget constraint, and we assumed, again, Napa and Alameda have budget, and only they do. However, their budget can be thought of like infinite, right? Or sufficient to cover the entire bay. So we're looking at, they could protect the entire bay, of course, and that would be optimal from a social point of view. But we were interested in looking at what different coalitions they could form. So we're showing, again, the Nash results in blue, and we're showing two different kind of cooperations. The counties involved in each of these cooperations, in addition to, of course, Napa and Alameda, are not all the same. So in fact, both collaborations, the orange one and the gray one, are possible. The benefit of the orange one over the gray one is simply that it has a lower cost. They have equal benefits. Whereas the yellow case is a cooperation that cannot happen. And it cannot happen for the simple reason that Contra Costa could not agree to it because it's worse off than in the case of Nash, right? All right, so these are results of what I just said. And, you know, really focusing, because we did many more cases than what I've shown, all of them, all those that had the highest difference between cooperation and Nash included Napa as a founding county, So Napa has money and it doesn't protect itself. It allocates it to protect other parts of the network, therefore minimizing travel time within the Napa segments. This has some similarity to the results we obtained with the central decision maker, where we showed that Napa and Sonoma did not appear on the Pareto frontier at all. It was not worth protecting them. So what we see here in the kind of game theoretic framework is similar. Another interesting result or consideration is that there are some cooperations that, if they take place, they lead to maximizing the benefit for the budgeting counties, those counties that are providing funding. Others are maximize benefit to the bay as a whole, right? There might be some overlap between them, but an example here is shown here in the Coalition 1 case and Coalition 2 case, and comparing them to Nash. So if the founding counties, Marin and Solano, just protected themselves, that would provide the best total benefit for themselves, right? But from the point of view of the bay as a whole, all counties, then obviously this third coalition would be better. So there's an interesting policy question here, is how might you motivate counties to take actions that are beneficial for the whole, and they would benefit as well, but would not necessarily maximize their own benefit. All right, so these are broad conclusions from what I've presented and other work we've done. And really the two most important points are this, is that in pretty much in every case we have compared Nash to competition. We have found that cooperation versus competition, we found that the cooperative games in almost all cases provided higher benefits than the competitive games. The other thing which is important is something I alluded to. It can also be cost saving in addition to improving benefits. So, moving on. So as I said at the beginning, we were also going to present some work that we did using finer levels of analysis than counties, right? So you imagine that a central decision maker allocating resources to different counties does not sound very palatable from a policy point of view and very unlikely to be acceptable. But if, on the other hand, the resources were allocated not to counties, but to protect segments of the bay, then that might be more palatable and more defensible. And the way we're doing that, it was about a year after we started our research that the concept of OLUs started to be applied to the Bay Shore in San Francisco. And there are two agencies, the San Francisco Estuary Institute and SPUR, the San Francisco Planning and Urban Research Association, that got together and were able to identify these homogeneous segments that are homogeneous from a hydro and geological point of view. And as a result of that, we can now start to work, instead of counties, but to work at the level of these OLUs. This is how they look like. There's something a little confusing in this map, is that the boundaries of the counties are kind of a simplified geometric shape, but the shape of the OLUs is shown here very clearly. And there are 30, they ended up with 30 OLUs. Essentially, each of these is a homogeneous segment, and some of them are more important to protect than others. So if you start to work with OLUs, then the central decision maker can say that we're going to protect OLU number 1, 5, 10, and 15, because protecting these will maximize benefit to the network, as opposed to I want to fund this county and that county. Obviously what we could not do with the 30 OLUs is to look at all possible combinations like we did earlier. There it was 2 to the power 8, here it's 2 to the power 30. Clearly that's not computationally something that we wanted to do as a research team. You see here that some OLUs fall entirely within one county, some straddle county, but we wanted to focus on San Mateo. Now, Marin is, as a county as a whole, can always be assumed to be protected because it's so important. San Mateo is the second most important. It has 5 OLUs. And the table I showed earlier, if you remember, showing kind of the benefits on different points on the Pareto frontier, showed this, right? Marin, then San Mateo, then Santa Clara, 0 for Napa and Sonoma, and small numbers for the other 3. So we decided to look at an analysis of the OLUs that fall within San Mateo, right? And identify which are the most important to protect, right? So in doing so, we're taking the rest of the counties as independent units. So it's a hybrid analysis, if you will. The forcing, the hydrodynamic forcing, is done at the level of the counties. The protection is done at the level of the OLUs, and only those of San Mateo, because as I said, these are the second most important. We start with some kind of basic assumption that Marin should be protected, and the results we showed earlier prove that. Santa Clara can either be protected or not, so we're going to look at these 2, and then we're looking at the 5 OLUs. And for the 5 OLUs, we're doing a marginal analysis. We're computing the marginal benefits rather than the average benefits. What does that mean? Is that we turn protection for each OLU one at a time, assuming all the others are not protected. An average analysis would look at turning a given OLU and looking at the average of all the other combinations of the 4 other OLUs protection, right? So in that sense, it's a marginal rather than an average analysis. And so that's the first thing we did. And then we wanted to do some interesting, I'm not showing you the results of that initial analysis because they're incorporated in this. We wanted to see whether it was possible to identify separately, to separate the effects of, because there are two things at play here. If you, in terms of vehicle hours of travel, in total travel time, there are 2 things at play. One of them is that you have, let's say, one county protecting itself, and if it's protecting itself, it adds to inundation in its neighbors, thus leading to additional congestion there, and that we can call this a hydrodynamic effect. The other one is if the county, let's say, does not protect itself, gets inundated, and then you have traffic spillback, you have congestion propagation from that county to its neighbors. So by this is what we mean by hydrodynamic versus traffic effects. I mean, both of them include traffic, right? But the source of the congestion is different. So we came up with these definitions to differentiate between these 2 kind of effects. So hydrodynamics on, and so again, we're looking at Santa Clara here and its neighbors in San Mateo, the 5 OLUs in San Mateo. So hydrodynamics on means that Santa Clara protects itself, but the San Mateo OLUs, as a result, experience additional flooding, which leads to additional delay. So that's a hydrodynamic effect. Hydrodynamics off is the opposite. And then traffic on means that Santa Clara is unprotected, therefore it gets inundated, and then traffic congestion propagates from Santa Clara to the San Mateo OLUs, right? Now, in reality, you have only 2 real cases. A case that combines hydrodynamic on and traffic off, where essentially Santa Clara is protected, right? Because if it's protected, that means that it causes inundation in San Mateo that leads to increase in congestion in San Mateo, but because Santa Clara is protected, there's no congestion propagation from Santa Clara to San Mateo, right? And then the other possible case is this and this. The hydrodynamics is off, which means the traffic is on, right? Now, in order to separate traffic from congestion, because these 2 cases are very clear, the 2 go together, we wouldn't be able to do that. So we created two auxiliary cases. So what you have here, these are the two real cases, right? And we have these auxiliary virtual cases, right? Where, so the one at the top is the best of both worlds, right? Everything is off. The hydrodynamics is off and traffic is off. That doesn't happen in reality. But we are able, by some tricks, not very complicated tricks, to obtain the VHT associated with that. And then, this is the worst of both worlds, where both effects are on. And then if you take the differences, which are represented by the links here, between the total VHT benefit for each of the boxes, you can separate traffic from hydrodynamics, whether Santa Clara is protected or not. So as I see that I'm approaching the end of my time, I'm not going to go through the details of the procedure to do that. I should say this is fresh off the press. I got these results, as I was telling somebody, Friday I think it was, and I prepared these last slides on the plane. So I will not go through these details. There's probably several typos. Just want to say two things. Now, the total number of commuters in the San Francisco Bay is on the order of 2 million. And so simulating all of this with MatSim would take an immense amount of time. So we're taking a random sample of 16% of the commuters, but we're also adjusting the link capacity and jam density accordingly, so that the scaling is done on both the demand and the supply side, all right? So if you take 16% of the population and you essentially use the scale factor for capacity and for jam density, you have essentially a real representation of the network. You're not cheating, in other words. And we compare the marginal benefits to base cases. And there are two base cases. I want to show these, even though they're not essential for the results, but just to give you a visual idea of what happens in cases of lack of protection. So there are three bridges that cross the bay in the southern part of the bay. This is a Bay Bridge. There's a bridge that doesn't appear here, which is the San Mateo Bridge, and this is the Dumbarton Bridge. So if Santa Clara is not protected and San Mateo is not protected, the Dumbarton Bridge essentially disappears. It doesn't mean it's flooded, it means it's inaccessible. So the approaches to the bridge on both sides are flooded, and therefore that link is inaccessible, so we removed it from the network. The Dumbarton Bridge, however, still operates. Now in the other case, when Santa Clara is protected, you have the hydrodynamics effect taking place that end up inundating the approach to the Dumbarton Bridge as well. And so therefore you have link cuts for both bridges, and you're left with only the Bay Bridge, right? And this is partly why the protection of San Mateo appears to be so important. So jumping directly to the results of this analysis. Again, this is the diamond I showed you a minute earlier. And for each of the links here, we have a picture next to it, and that picture describes the difference in benefits between the two boxes that fall at the two ends of the link. Okay, so two things. First of all, if you compare the top half to the bottom half, something is obvious and expected. That is, the benefit, the difference in benefits is positive for the top half, because you're comparing an ideal case which will never happen, that is, everything is working for you, to the real world, which is one of these two. And so the difference is positive. In the bottom half, it's negative, obviously, right? We have two hydrodynamic pictures, hydrodynamic effects picture, and two traffic effects picture. One corresponds to, so on the right side, I always get this wrong. On the right side are those that correspond to this case. That is, hydrodynamics is off, which means Santa Clara itself is unprotected. And what you notice is that the traffic effect is kind of fairly, there's no pattern, right? That is, the two most important counties, OLUs to protect are those that are simply the larger and therefore have most of the transportation network. On the other hand, the hydro effect has a very clear trend. The biggest effect of protection is in the OLU that's the closest to Santa Clara, that is the southernmost. The same thing happened in the two cases that correspond to this, where Santa Clara is protected. Again, in the hydrodynamic effect, there's a very clear trend. The biggest benefit comes from protecting that OLU, the southernmost OLU. Whereas in the traffic effect, the biggest impact, negative in this case, but the biggest impact falls in the same two OLUs as here, because these are the largest geographic regions and contain most of the traffic. Okay? So, conclusions are just repeating what I said, but really, I mean, the use of the OLU and the use of a traffic simulator, this is an agent-based simulator called MatSim, really allow you to do things that are much you do finer analysis than you could have done if you only used counting. Extensions. So the most obvious extension is to look at the other modes of transportation. And in particular, in the Bay Area, public transportation, the most important component, the backbone of the public transportation system is BART, the Bay Area Rapid Transit. Right? So the Bay Area Rapid Transit, it connects, and its initial design when it was built was to connect the East Bay to San Francisco and the peninsula. It was to take commuters from the East Bay, right, to who had jobs in San Francisco or south in the peninsula. Now, since then, it has expanded significantly in the East Bay, beyond the East Bay Hills, and it now goes all the way to San Francisco Airport, as many of you will know. Now, if if the Bay Bridge was inundated, for example, or the approach to the Bay Bridge was inundated, BART would end up carrying all this traffic, right? And vice versa. If the BART tunnel, the Trans-Bay Tunnel, right, this is the tunnel that connects the East Bay, that takes all BART trains from the East Bay to the San Francisco and the peninsula. If that were inundated, then these people would end up driving. So we've done some preliminary analysis. I'm not comfortable showing them but that shows that the second case is much, much worse. That is, if the BART tunnel is inundated, the total vehicle hours travel or person hour travel, assuming everybody drives alone, is on the order of 50% increase. But if the Bay Bridge is inundated, then the effect on total VHT is much lower. It's on the order of 10%. And the reason is obvious. Public transportation is a much more efficient means of carrying people. You can jam more people in less space. They take less road space. And therefore, the effect should be much higher if all these BART commuters had now to drive using the Bay Bridge or other points, adding congestion to everybody. Other extensions, now more long-term, if maybe one can accept the assumption I haven't stated, but that's implicit, which is that the land use pattern is not changing in between now and 2050. So that the OD matrix that describes how the demands is stable. But that certainly cannot be true if we move towards the end of the century and we're talking about 1.5 meter sea level rise. In that case, clearly what you would expect to see is that land use patterns would change. And as they change, the result is going to be that the OD matrices will change. Now, to predict that kind of evolution requires kind of a good urban simulator like UrbanSim. And we've been talking to the developer of UrbanSim, Paul Waddell, who's a faculty member in planning at UC Berkeley, about maybe the next phase collaborating on looking at that. And then we haven't even started talking about all the other types of infrastructure that are also important. So these are some of the publications of just the NYU team. There are about twice as many from the Berkeley team. And so for those who are interested in kind of the math side of the game theory aspects, they're described here. What I've presented comes mostly from a publication in this journal, in Journal of Transportation Policy, looking more at the policy side. And this was the first paper that we wrote that focuses on a central decision maker. And this is some of the later work, not what we presented, but other works related to OLUs. And with that, I end my presentation on 5:59. I still have 1 minute. Happy to take questions. Ali, yes.
So I had a question on the theoretic part. Sure. I was wondering, would it make, to me, it kind of makes sense that maybe the game should be a game of strategic substitutes, where, because there's clearly externality between different municipalities or counties.
Yes.
So you would want to, basically, the action of others, you might feel like, okay, the others are taking care of me.
Yes.
So in all investment games, you have the situation where other people's investment might dissuade you from.
Yes.
Yes.
No, this is an interesting consideration. In fact, one of the reviewers of the paper said, you ought to be looking at that.
That wasn't me, by the way.
Not accusing you. This was it was a productive review, constructive. But certainly, so you have these kind of incentives to do the wrong things, right? But we didn't take that into account. Yes, Eric.
Thank you. When you say inundated, are we talking about inundated under mean conditions, under high tide?
No, high
under
tide.
Extreme high tide?
No extreme events. So no king tides, no storm surges. We're looking at fairly steady state conditions. So, the usual high tide.
Just astronomical.
Yeah, nothing like king tides is something that actually Mark and his student, Michel Hummel, are actually now looking at, also trying to introduce extreme events in the analysis, but we haven't done that.
And to what extent are your calculations validated?
I'm sorry?
How do you validate the models?
Oh,
Both
the traffic
hydrodynamics
models?
and the people models.
And the what?
The people models.
And the people models. So on the traffic side, the user equilibrium model is kind of the state of the practice. It stopped being the state of the art more than 20 years ago. But most of the improvements have to do with kind of looking at dynamic conditions, which we're not interested in. This is more of a planning level of analysis, not an operational level. Now, what's the assumption in user equilibrium? It's fairly standard, is that everybody takes from the origin to destination the shortest path, but that at equilibrium, right, no one has an incentive. It's in fact a Nash situation, right? Is at equilibrium, no one can reduce their travel time by unilaterally changing routes. It's an idealized approach to traffic assignment, but it's kind of the state of the practice. It has other issues with the traffic realism. So there are no physical cues in user equilibrium. The cues are vertical, so there's no. There are many issues, we can talk about them, that are problematic with user equilibrium, but it's from a practice point of view, this is what's used and accepted. Validating the Cosmos prediction. We're talking about the future and 0.5 meters, so we don't have data, right? It's fairly well calibrated in the sense that for the 0 meter sea level increase, There are, I didn't say that, but there are a few segments of the bay, especially around San Francisco County, which are currently protected, right? And so Cosmos does a fairly good job of replicating current conditions. Now, the improvement we've made since then, and your student Aaron was instrumental in that, as we're looking at what would happen if the BART tunnel is closed, we need a much finer level of resolution of the grid. So from an average of like 500 meter grid size, we're going to 50 meter. And the results change. So all this to say is that this is not a Bible, right? It's as good as what we had for the analysis.
Other questions?
Yes, Fred.
Where do you assume that the money is coming from? Because implicitly, you're acting as if the counties decide what to do. So you're assuming it's a property tax of the county?
So in the case of a central decision maker, really here we're looking at, what if FEMA came, the federal government or the California government came with the money. But in the game theoretic cases, then yes, we're assuming that this is things like property tax that's being diverted for protection, which might explain why San Mateo are ahead of everybody else, because it's a fairly rich county.
Because I think it, if you assume that it's some kind of a carbon tax imposed either by the nation or the state of California, then it falls more easily into a central decision maker trying to make these decisions. And this kind of analysis could help to build the political will to do that.
Mm-hmm.
The opposite assumption that it's the local property tax paying for it, it seems to me the problems of irrationality get much, much higher, where people, don't react to what the bottle says. They don't react. But in that sense, looking at what happens with king tides, because that's the wake-up call.
Yes, it is.
That will happen much earlier than these averages. So it maybe you want to sort of look at these two alternative possibilities.
Right. I mean, I think it's your question really fits you've articulated it better than what we had as the two different approaches. One where you have a centralized decision maker, and the money could come from a carbon tax. Though, again, if you talk about the state of California as a whole, people in Irvine will be wondering why they have to pay for the protection of the San Francisco Bay by raising their carbon tax. But in the case where you have these game theory models we had, then the assumption is the county has raises its own revenue.
Yeah, well, you could even make an assumption that if you had a carbon tax, that the revenue is attributed to counties in an as-if to do the analysis, so that you don't have this region taking the money
From yes.
You can let the region sit on its own bottom, but you get rid of the individual county
Right.
problem.
So the good thing about our research is my colleagues, Mark Ceci and in particular Bruce Riordan, who heads an organization on campus at UC Berkeley, is in constant dialogue with decision makers. In fact, we're starting to really publicize this work in the hope that it would raise awareness, partly, and also that it provides alternative models of combating sea level rises, of protecting cities from sea level rises. So in the end, this research is interesting from an academic point of view, at least to us. But it aims to really have an impact on the debate, and we've made some small inroads in that direction. Yes.
So I just want to piggyback on that briefly. One comparison I was missing, maybe I missed something here, was that between the benefits of the central decision maker model and the best that a group of counties could do, because that seems to me that's almost one of the biggest takeaways from this. If there's a gap there to say, look, you central decision makers in Sacramento, I think that's more realistic than Washington, but you know, look, there's some welfare being lost here, and there's an argument to be made for you stepping in. Do you have a brief description you could give us of the best that can be done in the central decision making model that you had at the beginning versus the best that the counties can be done?
So this is an interesting thing and something that you'd think would be obvious to do, and we haven't done it. But the numbers are there. It would be fairly easy to do that comparison. And I'm kind of surprised we didn't think of. We're so focused on Nash versus
You need to talk to
cooperation.
political scientists more often.
But yeah, I should. But absolutely, that's an easy comparison to do. The problem, of course, with the central decision maker when we apply it to the county level is that it's frankly politically unreasonable to expect that the central decision maker would allocate resources, limited resources, on a county by county level. I mean, there's no way politically that this can sell, right? Which is why the concept of oil use is useful. It's because with oil use, you know, it's not your entire county we're protecting. It's no county, you know, some counties may get no protection whatsoever, but it's based on something physical rather than some abstract mathematical model. You know, it's like, you know, if we don't protect this, we all suffer. And I think that might be easier to accept. Thank you. Sorry.
Yeah, so just one question, two questions related. So in terms of separating the two effects with respect to the traffic versus hydrodynamics,
Yes.
there would be interplays in reality between the two. So what is the main reason to kind of have separation, to investigate the separation between the two? That was the first question.
Okay. So as I said, in the real world,
Yeah.
you can either have case one or case two. Right? And in both, and that's it. So you can never separate, right? But it's interesting. So it's interesting really not from a policy point of view, from a scientific point of view to us, to understand how much of the total benefit or disbenefit happens, can be attributed to traffic versus hydrodynamics. In the end, it makes, nobody cares in practice, in the real world, because it's like, oh, okay, so traffic is more important, let's say, than hydrodynamics. So what? It's simply interesting from a kind of like trying to understand what goes within the analysis, because every time, all the cases we did, there is a hydrodynamic effect which leads to some additional traffic congestion in other parts that are unprotected, certainly, right? So your question is a valid one. But we were curious, really, to try to see how much is attributed to traffic versus, and how the combinations of protection change. This versus this, for example.
And my second question was related to the effect of inundation/sea level rise on the traffic. So if I look at, for example, historical PEMS data, there would be kind of flooding of bridges or flooding of some structures, some disruptions.
Yes.
So would it be reasonable to assume that if I were to investigate the response of traffic after PEMS, using PEMS data, let's say in steady state, I will largely gather the same effects, or is there something specific with regard to the coastal inundation that
is different to
for example, flooding of the bridge
or an earthquake?
Oh yeah, sure. Yeah.
Right. No, I don't think there is a difference. The cause of the specific natural hazard, I'll tell you what is different. The only difference is that the structures that are going to be, and the links that are going to be affected are those near the bay, right? Whereas, let's say if you had an earthquake, it's probably the bridges, or, it might not be the same links.
So inaccessibility is the main reason, and so long as we're able to capture the inaccessibility.
Yes.
The coastal hazard, and that is the effect on the traffic will be responding to the inaccessibility.
That's right.
Okay.
have a last question about, like, when you say hydrodynamics on and traffic is off, what exactly do you mean by hydrodynamics on or off?
Traffic. Yeah, I wrote it, and I obviously went way too fast over that slide. All right. So hydrodynamics on means that they're happening. The hydrodynamic interaction is happening. And that happens between, again, we're looking at Santa Clara versus the OLUs in San Mateo. That means that you're protecting Santa Clara. And as a result, you have added inundation in San Mateo because you're diverting, the flood to your neighbor, right? And off is the opposite. Santa Clara is not protected, and therefore there's no effect from the flooding in Santa Clara on the flooding in San Mateo. Traffic is saying, if the traffic is on, essentially what it's saying is that Santa Clara is not protected, so there's inundation of some of the links in Santa Clara that causes congestion, and that congestion then propagates to San Mateo. Right? So for example, you have queues that spill back into San Mateo, or route diversion that happens that leads to added congestion on San Mateo.
I would say if you make the hydrodynamics scenario more complicated with how big of the flood, or it would be really interesting to see like various different scenarios.
To go beyond 0.5 meters, so look what happens at 1 meter and 1.5, absolutely. There's still a lot of territory. This research has been going on for 3 years. And every time we get to a point, we say, how about we look at that? So the number of questions that we've answered is minuscule compared to what the other questions that can be asked.
All right, this was the last question. We leave for the 15 minutes of discussion will be here. So if you have more questions, you can come up to the speaker. Thank you very much.
Thank you, Lydia.